Hey everyone, welcome back and let's write some more Leetcode today. So today let's solve the problem minimum cost for tickets. And before we even get into the problem, when you see a keyword like minimum or maximum or number of ways or anything like that, you kind of have a hint that the problem is going to be DP related, dynamic programming related. But let's just continue on and I'll kind of explain why dynamic programming is going to help us with this problem. So we're given an integer array of days, and each day within this array is going to be sorted, right? So we're going to have a list of days, let's say 1, 2, 3, and basically it's going to be a sorted array, and it could have integer values anywhere within the range between 1 and 365. So it's days within a single year. Now it doesn't have to have those, right? We could have 1, 2, 3, and then 100, right? These are the days within the year that are going to be in this array, right? It could actually have every single day from 1, 2, 3 all the way to 365, right? It could, but that's just kind of the possible values we could have within this array. We're given a second array as well. This second array is always going to be of size 3. It's going to have 3 different values. The first value is going to represent the cost it takes to purchase a 1-day pass. What does a 1-day pass do for us? Well, we're given this integer array of days. This 1-day pass will allow us to travel for 1 day. So suppose on day 1, right here, on day 1, we purchase a 1-day pass. That means, okay, we have our travel covered for day 1, right? But now we're on day 2. So we're going to have to purchase another 1-day pass if we want to be able to travel on day 2. Basically, this array of days is just a list of days that we want to be able to travel on. And this second array is going to be the cost of the travel pass that we need to actually be able to travel. Now, the difficulty here is we are given a choice. We're given 3 choices of travel passes that we can purchase. We can purchase a 1-day pass, we can purchase a 7-day pass, or we can purchase a 30-day pass. Now, a 1-day pass is straightforward. A 30-day and 7-day pass is a little bit more tricky. So for example, a 7-day pass in this case, suppose we purchase a 7-day pass on day 1. So that covers our travel for day 1, for day 2, for day 3, for day 4, 5, 6, and 7, but notice how 4, 5, 6, and 7 aren't even inside of this array. That means we don't even need to travel on these days. So one possible choice you might be noticing here is we could have done this 2 different ways, right? We could have purchased a 7-day pass, which would allow us to travel these 3 days that we need to travel on, or we could have purchased a 1-day pass on this day, a 1-day pass on this day, a 1-day pass on this day, and even a 1-day pass on the last day. Or like I said earlier, we could purchase a 7-day pass to cover these 3 days and then do a 1-day pass on this day. And basically, as the title states, we want to know what's the minimum cost it's going to take for us to travel all these days. So the first thing we should do with a problem like this one is just try to determine a possible solution, even if it's inefficient. Let's start out with the brute force approach and then see if we can even come up with a solution that works. And then from that brute force, let's see if we can optimize it any way possible. Okay, so let's take a look at the first example that they gave us. So this is the days that we want to travel on, and this is the costs array. So the first value 2 is if we purchase a 1-day pass, 7 is if we purchase a 7-day pass, 15 is if we purchase a 30-day pass, right? So this is the price. And we want to know what's the minimum cost to travel all these days given these choices. So let's just brute force start making our choices, right? And you guys know I like to do a decision tree for that. So let's say that we start on day 1, or in other words, we start at index 0 of this array, right? Day 1 is what's at index 0. And we could purchase a 1-day pass, which would cost us $2. We could purchase a 7-day pass, which would cost us $7, or we could purchase a 30-day pass, which would cost us $15. Now, obviously, if we purchase a 1-day pass, instead of being at day 1, we're going to be at day 2, right? But now the important question you should ask is, is day 2 even in the array of days that we want to travel on? Well, we don't even want to travel on day 2, right? So who cares? Skip day 2, right? Do we want to travel on day 3? Nope, it's not in the array, is it? So in reality, when we purchase a 1-day pass, all we really need to do is go to the next position in the array, right? We started at position, at day 1. The next position is day 4, right? So let's just go automatically to day 4, right? Day 4 is the next day that we actually want to travel on. And if we purchased a 7-day pass for $7, then the next day we would want to travel on is day 8, right? 1 plus 7 brings us to day 8. Now, in terms of how we're actually going to do this algorithmically is we're not just going to assume that day 8 is a day that we actually want to travel on. It could be that day 8 isn't even available. Let's go back to our array, right? Starting at position 1, we're going to go to the next position until we get to a value that is greater than or equal to day 8. Because, we purchased a 7-day pass, that means we traveled on day 1, we can travel on day 2, 3, 4, 5, 6, and 7, right? But so basically we have a travel pass that can cover these days, but we can't cover day 8 and beyond, right? If we want to go to day 8, 9, 10, we can't cover that with a 7-day pass. So we'll have to purchase another pass. So that's what I'm getting at over here. So let's go back to our array. So from day 1, we can go to day 4. Yep, we can cover that. We can go to day 6. Yeah, we can cover that. Day 7, we can cover that. But then finally, when we get to day 8, we can't cover that with a 7-day pass. So day 8 is going to be the next day that we look at in this decision tree. Now, if day 8 wasn't even in this array up above, if day 8 was not there, then we could automatically skip all the way to day 20, right? Because we don't have to travel on any days in between 7 and 20. Then we can just skip there, right? That's kind of the logic that I'm trying to get at here. So with the 7-day pass, we get all the way to day 8. Now with a 30-day pass for $15, we can actually skip every day here, right? Because with a 30-day pass, we can go through days 1 through 30, right? So if we iterate through this array, day 4 is covered, day 6 is covered, 7, 8, 20 is also covered with a 30-day pass that we purchased on day 1. So we actually covered the entire array, right? So there's nothing left. So basically, this is one solution that we can, at least one path in our decision tree, right? If we just purchase a 30-day pass, it'll cost us $15 to arrive at the destination. So the question now becomes, is that the minimum? Well, we don't know for sure because we haven't fully gone through these 2 other paths yet. So now that you kind of get the main logic of the decision tree, I'm going to go kind of quick. So I'm just going to tell you that this is the path that's going to lead us to the correct decision. And, we could purchase a 1-day pass, which would bring us to day 20. And the cost of that would be $2. So then we'd be at day 20. Or we could purchase a 7-day pass for $7. And that would put us at, the end, right? Or actually, that would not put us at the end because then we'd actually, again, be at day 20, right? Because from day 8, 7 days is not enough to also travel on day 20. So you can kind of already tell that this path is the same as this one, except this one just costs more. So this is probably not going to be the solution. And from here, we also have a choice. We can purchase a 1-day pass or a 7-day pass or a 30-day pass. But since there's only 1 day left, day 20 is the last day, of course, we're going to want to purchase a 1-day pass, right, for $2. So let's draw that over here. And then we get to the end. So what was the overall cost of this entire path? It was 7 plus 2 plus 2, which puts us at $11 for this path. This path was $15. With this path, we could purchase a 7-day pass for $7 and then purchase another 1-day pass, but that would pretty much be the exact same as this path, which would also be $11. So $11 is the minimum. You can see that there are, potentially multiple solutions that would lead to the same result, but it doesn't really matter because all we want to return is what was that cost, right? We don't want to know what days did you purchase the passes and all that. We just want to know what was the cost. In this case, it's 11. Up above, you can see that they had a similar explanation, and the result ended up being 11, which is the minimum. The good thing here is that we did find a brute force approach. What is the time complexity of this? You can see it's a decision tree. We could have 3 branches on the decision tree, which gives us 3 as the base. Now, what could be the height of the decision tree? Basically the length of days, right? Because we'd have a branch each time we get to a new day. So overall, you could say the time complexity is 3 to the power of n, which is not very good. It's exponential, but is there any way we can eliminate repeated work in this problem? Yes, we can, and there's a couple tricks to doing it. So you can kind of tell that, the node values that you see here, what determines, the node value, for example, 1 or 4 or 8, what determines that? It basically is determined by the index I that we are at currently in our days array, right? If we're at index 0, then we're at day 1. If we're at index 1, then we're at day 4. If we're at index 2, we're at day 6, etc., etc. And that's really the only parameter we're going to have to pass into our recursive DFS solution, right? I is the only parameter, the index of the day that we're at, because our costs are always going to be the same. This is never going to change or anything. So I is the only parameter we're passing in. So then how many, if we cache this, hopefully you are familiar with caching. Basically, if we find the result of, let's say DFS, we call DFS starting at index 2. If we find the result of that, we don't want to recall DFS again, because you can see that that might be the case with a really big tree like this. We might end up, from here, you can see that these two parts of the tree end up calling at the exact same index. So we don't want to do repeated work. So we can cache that. So if we computed DFS of 2, we'd put that in a hash map or a cache or some kind of data structure, and then we wouldn't have to repeat it again. So if we only compute the DFS from every single position index I, how many times are we going to be calling DFS? Basically, the size of the input array days, right? So the actual time complexity is going to be roughly big O of n, because n is the number of times we're calling DFS. Now, each particular call of DFS could be inefficient, right? It could have its own time complexity. So maybe O of n is not accurate. But it turns out that the way we're doing it, if we purchased a 1-day pass, we'd only look at the next position and then we'd be good. If we purchased a 7-day pass, then we'd have to potentially look at the next 7 positions of the array. If we purchased a 30-day pass, we'd have to potentially look at the next 30 positions of the days array. So technically, the actual time complexity of this could be not n, but rather 38 times n. The way I got this 38 is basically 1 plus 7 plus 30, because that's how many operations we'll have to do within a single DFS. That'll probably make more sense when we write out the code. But what I'm saying is the time complexity is still big O of n, even though we have a constant value here. I think this is all you really need to know to jump into the coding solution. So let's do that. Okay, so now let's do my favorite part, the code, because we don't have to draw anything. We can just write it out. Let me know if you made it this far into the video. Make sure to like and subscribe. It really helps out the channel a lot. But so the first thing we want to do here, as you can see, is our cache. I call it DP. You could call it cache or whatever you want. This is just so we don't have to do repeated work. Now let's write out our recursive backtracking or DFS function that we are going to be implementing with dynamic programming, because we're using a cache. And remember, the only parameter we need for this is just the index that we're at in our days array. Now, let's not forget about the base case. What if we go out of bounds? Well, if I reaches the end of our days array, then what are we going to return? We're going to return 0, because what we're saying is if we don't have to travel any days, right? Like if there aren't any days left for us to travel, how much is it going to cost? It's going to cost 0. The second base case is if this has already been computed before, meaning if I is in our DP cache. If that's true, then we're going to return DP of I, because it's already been computed. We don't want to waste time recomputing this work. The next thing we want to do is initialize this DP of I equal to a default value. And since we're looking for the minimum, a good default value for this will be infinity, because then if we compute a different value, it'll obviously be reassigned to that smaller value. So initially we'll set this to infinity, but we're obviously going to compute it based on the 3 costs that are available to us. So let's iterate through that costs array, and we're going to do it simultaneously with another array. And so basically some Python magic is we can zip an array, basically iterate through 2 arrays at once. So one is we want to know for the prices, how many days can we actually travel? We know that that's 1, 7, and 30. So that's one array. The second array is going to be the actual cost associated with each of these, durations. So we're going to be iterating through these two arrays simultaneously. So D is going to be the number of days we can travel, and C is going to be the cost for traveling that number of days. And here's where things get a little bit tricky compared to other DP problems. So you might be thinking, okay, we want to know what's the cost to, starting from day I to travel all the remaining days in the input array. Can't we just compute that with, let's say, obviously we want to find the minimum, right? So let's take the minimum of whatever it is itself, and then also, recursively say, okay, well, the cost if we purchase this current day pass is just going to be, okay, C plus DFS of, let's say, I plus D, right? That might be your first guess because I is the current day, and then D is the number of days that we purchased the pass for. But remember, like I showed you in the example, what if we had an input such as 1, 2, and 8, right? If we purchase a 7-day pass on day 1, that'll cover day 1, that'll cover day 2, but it's not going to cover day 8. And remember, the parameter that we're passing into our DFS function is the index of the value, of this day's array. So we can't pass in day 8 and expect to get here. We'd actually have to pass in index 2 to get to this spot. So we're actually going to, before we even run this, we're going to have to do some pre-work. We're going to have to find that day. Basically, we're going to run a while loop starting at day I, wherever we're at, and keep incrementing until we get to a day that would be out of bounds. So for example, if we purchased a 7-day pass, day 8 would be the first day that's out of bounds. So let's use a different pointer to determine that. We're going to use a pointer called J. It's initially going to be set to I, and we're going to increment this pointer J while it has to, of course, be in bounds. So while it's in bounds of the days array, and while days at index J is less than whatever day we can travel to with the purchase pass that we're iterating through right now. And how do we determine that? Well, it's going to be days at index I, right? That's the current day that we started at, plus how many days can we travel? We can get that with D, right? D is that parameter. So days at index I plus D, this is the day that we can travel to. So for example, if we start at day 1 and we had a 7-day pass, 8 would be the value that this evaluates to. And then, our pointer J would keep being incremented from this array until we actually arrived at this position. So this while loop is just kind of incrementing J plus 1. And then finally, when we have J at the position that we want it to be at in this DFS, that's what we're going to pass in. We're not going to pass in I plus D. We're going to pass in J because that tells us what's the next day that we'll actually need to purchase a travel pass on. And C is the cost that it took us to actually travel to this position. So C plus DFS is, the computation that we need to do here. And after that loop is done, then we can go ahead and return DP of I. That's what we, spent all that time computing. And you might think that, is this an O of n time loop? No, it's not. This loop is going to run at most roughly 38 times because this while loop could execute once when we go through the 1-day pass. It could execute 7 times when we purchase the 7-day pass, and it could execute 30 times when we purchase the 30-day pass. So it's not a linear time loop. It's in, 38 times loop. But yeah, that's the entire dynamic programming solution, recursively at least. And then once we're done with that, all we need to do is actually call our recursive function that we just defined, and we'll pass in 0, because remember 0 or whatever, this value I is the index that we're starting at in the days array. Of course, we want to start at index 0 of the days array. It's not the day itself 0, it's the index. So that's the entire code. Let me run it to make sure that it works. And as you can see on the left, it does. It's relatively efficient. You might be wondering, what does the actual dynamic programming solution look like compared to this? And it's pretty similar. I'll just copy and paste it right now just to show you. So we'll use the exact same cache that we have above, but let me copy and paste. So this is the dynamic programming solution. You can see we're doing it without recursion. We're doing it, we're doing it backwards. The outer loop up above is going in reverse order, but you don't have to do that. The reason I do it in reverse order is just because then it matches up with the recursive solution, but you don't have to do it like that. You could do it front to back. But the rest of this is pretty straightforward. It's pretty similar to what we had in the DP solution. One thing I will mention is how the base case, in the recursive solution, when we go out of bounds, we end up returning 0. The way I handle that in the DP solution up above is dp.get, which is a Python function for hash maps. So I'm saying dp.get whatever is at index j. Now, what happens if index j is out of bounds? Well, then we're just going to return 0 as the default value. This is just a predefined function in Python that I'm using just to shorten the code a little bit so that we don't have to actually write out an if statement on this line. But other than that, I really hope that this was helpful. If it was, please like and subscribe. It really supports the channel a lot. Consider checking out my Patreon where you can further support the channel if you want. And hopefully I'll see you pretty soon. Thanks for watching.